The next property of systems that we are going to discuss today is what is known as the invertibility of a system. So what do we mean by invertibility? Invertibility simply means that trying to compute the inverse of the system. So we know inverse of a function. What does it mean when we say inverse of a system? It means that given a particular output of a system, we should be able to identify what was the input which generated this output. Then if we can do that successfully without any kind of ambiguity, then we say that such a system is an invertible system. So you feed in some input to your system, some x of t, and then you observe the output y of t. Now if somebody gives you only this y of t and then tells you this system, this box here produced this y of t, can you identify what was the x of t that gave this y of t? If you are able to successfully tell this for all possible outputs, then we say that this kind of a system is an invertible system. Now, can there exist systems for which this is not possible? Of course, it is not possible for certain kind of systems. For example, let us say now here you just give some x of t as some input, and let's say the output here is x of t the whole square. All the system is doing is just squaring it and giving you the output. Then can you tell what was the input? Let's say if the output was plus 1 at some time t is equal to 0. Can you tell what was the input at time t equal to 0? It could have been either plus 1 or it could have been minus 1. We don't know what it was, right? So in this scenario, this system is not invertible. Now, if it was a cube of the input, then we know what exactly would have been the input given this output. Now, if the output was plus 1 at time t is equal to 0, then let's say the output is 1 at t equal to 0, then we know that x of t should have been plus 1. If it was minus 1, then we know it should have been minus 1. So this is an invertible system. So depending upon what the system does, either from the output that is observed, you can tell what was the input, or you may not be able to tell what was the input. So whenever you are able to map back to the input just by observing the output, you claim such a system is invertible. What does it mean? It means that this is a lossless transformation. That is, whatever processing the system does to the input, that processing is a lossless process. Why is it lossless? Because just by observing the output, you are able to tell exactly what was the input without any kind of ambiguity. So because you are able to go back exactly to what was the input, this is a lossless processing or a lossless transformation. Now, if an inverse is possible, that means that inverse operation can also be modeled as a system, right? So now somebody gives you the output, you have to do some kind of mapping to the output to get back to the input, right? That mapping can also be seen as a system. In other words, a system is mapping the input to your output. Now, given that output, you can feed that into some other black box and get the input, assuming that it is an invertible system. So which means this F inverse here is another system altogether, okay? So now you can construct another system. Now what if you put these systems together, then whatever you feed in here as the input will always come here as the output. So if this is possible, if it is possible to construct such a setup, then we say that this system is invertible. Well, obviously this inverse is also an invertible system, right? Because this we say is one system and it does some kind of a mapping, and then there exists some other mapping which will revert it back. If you just change the places of these two boxes, then this operation will still work, meaning whatever you feed in here as the input will still come here as the output. So both essentially are systems where one is the inverse of the other, that's all. So an inverse operation basically is another system which converts back whatever is fed to it to the inverse map of the previous system that we considered, okay? All right, let's see some examples. Now, if there exists a system which takes input as x of t and produces an output y of t such that we just add a constant to it. So this is a constant. Is this an invertible system? It is an invertible system as long as the c is a constant. Why is it? Because given any output y of t, you can construct the input back by saying x of t is equal to y of t minus c. All you have to do is just subtract this c and you will get exactly the input. There is no ambiguity here, right? So this is the inverse system. So here, if you think of the system as some f, this is x of t and this is y of t. The inverse system in this case takes in y of t and produces x of t according to this equation. Okay, so this inverse is possible and hence this is an invertible system. This is an invertible system. Okay, let's see this case. Basically, this is the case where we are doing time scaling and shifting. So you feed an input to the system and this system that is, and the system all it is doing is just shifting the time and scaling the time and of course amplifying it to some gain. Now, is this an invertible system? Now, what do you think? As long as this a is not equal to 0 and of course small a is not equal to 0, this is an invertible system. Of course, this is an invertible system. Remember, because we found out earlier when we discussed about time shifting and time scaling in the signal analysis module, we said that given a shifted and scaled signal, there are set of operations which you can do to get back the original signal, which means we know exactly how to reverse it back, right? So because we know how to reverse it back, there is an inverse operation that is possible. So because the inverse operation is possible, we say that this is an invertible system. So the inverse operation here is, first you have to reverse the amplification or the gain 1 by a, and you have to modify the time t. In other words, you just say take t, subtract it and scale it accordingly. So if you can do this operation, then effectively here you have inverted back and then obtained. So because a is getting divided in both the cases, we need to have the small a and capital A to be non-zero, and that satisfies the existence of inverse. So hence this is also an invertible system. Excellent. Now let us see what happens to this case. Now, can we get back x of t as something like y of t minus c divided by t square? If we do this, will we get back the input signal? Well, it so happens that this is not an invertible system. It looks like it's an invertible system here, but what happens at t equal to 0? This goes to infinity, so we'll not know what was actually here in that case, right? So at t is equal to 0, y of t is not invertible. So even at one point, even at a single value of time, if you're not able to find out what was the input, then you say that the entire system is non-invertible. So this is non-invertible system. Okay, now let's take the next example. So the next example is simply cos of the input signal. In other words, can you try and get the fed in signal, the input signal, as cos inverse of y of t minus c. So as you can see here, all I'm trying to do is just get back to x of t by just rearranging the equation on this side. So observe this equation here. So clearly cos of anything plus 2n pi is still the same thing, that is cos theta plus 2n pi is cos theta itself. Cos is a periodic signal, which means you are not going to get back the original signal whenever the original signal's amplitude is going to cross 2n pi or 2 pi. So once again, this means that this is not invertible. Simple case, if x of t is 0, it produces the same output when x of t is 2n pi. So you will not be able to invert and then say that, okay, the value of x of t was 0 at this time or it was 2n pi at this time. No. So this is a non-invertible system. Now what about this system? It looks like derivative is an invertible system. It looks like you can just integrate. So what if you try to compute x of t as something like minus infinity to t y of some tau d tau. You basically integrate the signal that is given to you till the point time t. If you do this, can you actually recover back? It looks like it is possible, but actually it is not. Why? What if x of t is a constant? If x of t is a constant, then the output is 0 always. The derivative is 0 always, no matter what the constant value is. If c is equal to 10, the constant value will anyway after taking derivative become 0. So if t is equal to 100, c is equal to 100, it will still be 0. If c is equal to minus 120, after taking the derivative, this value is always 0, which means you will not be able to find out what was the value of c which gave this output. So this is also not an invertible system, which makes the integration operation also to be not an invertible system. In other words, if I say that y of t is equal to minus infinity to t x of tau d tau, the same reasoning goes on. So if you give a constant signal as the input to the integrator, then the output becomes infinity. In other words, let's say you have a signal which looks like this, which is a constant signal. So if constant signal has just a straight line, right? So this is c. So if you are going to integrate this from minus infinity till some point time, then the area is always going to be infinity, because this is a rectangle whose length is infinite and breadth is c. So this is always going to be infinite. So this output will be infinite for any value c. Because of this reason, you will not be able to recover back what was the original signal from the observed output. So this makes this entire setup, either the integrator or the differentiator, the two important systems that we discussed earlier, to be a non-invertible system. Okay. Now, what if you just multiply x of t with x of t plus t? That is, you multiply a shifted version of the input with the input itself. Is this an invertible setup? Now, can you think of somehow getting this x of t as some expression of y of t? That's not even really possible in this scenario, simply because this is a non-invertible system. A very simple way to verify this is, let us feed an input of a rectangular signal. I'm going to feed in, let's say, a rectangular signal to this system, and let us say that capital T is 1. Now, what is the time shifted version of this? The time shifted version of this, because capital T is 1, it's going to move to the left, right? Now you multiply these two, you're going to get 0. So if you feed in a rectangular signal like this, and then you're going to get a 0 as the output. Now let's say it is not rectangle, but then it was a triangle, something like that. Even then, now it is also going to be 0. So no matter what, the output here is 0, irrespective of that being a rectangular signal or a triangular signal. So you will not be able to know which was the input that gave us the 0 output. essentially making this a non-invertible system. So if you are asked to find out a given system is invertible or non-invertible, to say that it is non-invertible is very easy. All you have to do is given two inputs such that their outputs are same. So if you can find two inputs x1 and x2, if there exists x1 and x2 such that f of x1 is equal to f of x2, then you can safely prove and say that this system is non-invertible. Proving something is invertible is a trickier part. For that, you will have to find out what is this F inverse, like how we did here, how we did here. You will have to say, okay, the system is invertible because there exists an F inverse, and this F inverse is of the form something like this or something like this. Okay, so if somebody asks you to design a system and check if it is invertible, you will have to find its inverse. And if it is non-invertible, you will have to come up with at least two signals like this and then say that they have the same output. Because of this reason, I won't be able to know which one was the actual input which produced this output, and hence the system is non-invertible. So this is the way that you say a particular system is either invertible or non-invertible.